So we have developed self-healing concrete. This is a concrete which, when damaged, can reheal itself.
The concept of self-healing materials emerged. So can we turn the non-living concrete all around us into living systems?
And while concrete is the world's most used building material, it is prone to cracking, and engineers are always trying to improve its durability. And scientists in Ecuador say they have done just that with help from a rather surprising ingredient. Dan Collins explains.
Any engineer will tell you the problem with concrete is that it cracks. Now there's a concrete which has the solution mixed right in, using a living ingredient.
What about self-healing concrete? We were talking about that in our morning meeting. And I mean, when I heard about this, I said, wait a minute, what? There's a crack and then it naturally heals? Do you guys make that?
We do, yeah, absolutely.
A thin crack on a bridge or basement wall is easy to ignore. It looks like a pencil line. But that tiny line is often the first step in a long, expensive chain. Water gets in, winter freezes it, metal inside starts to rust, and the crack slowly grows. In the United States, the American Civil Engineers, also called ASCE, has been sounding the alarm for years. In its 2025 Infrastructure Report Card, released on March 25, 2025, it frames aging systems as a national challenge. In the bridges category, it notes an average bridge age around 44 years, with a large share already 50 years or older. That matters because concrete structures are not meant to be set and forgotten forever. And it's not just bridges. Concrete roads, tunnels, parking garages, seawalls, and apartment blocks all fight the same enemy: tiny openings that let water and salts called chlorides travel deeper than they should. Once that happens, the damage can speed up quietly under the surface. Concrete is strong when you squeeze it, but weak when you pull it. So cracks are not rare accidents. They're a normal part of concrete's life, caused by shrinking as it hardens, heat and cold cycles, heavy loads, or ground movement. Here's the scary part. A crack is not just a line, it's a doorway. When water and salts reach the steel bars inside reinforced concrete, that steel can corrode. Rust takes up more space than the original steel, pushing outward and cracking the concrete cover, which can lead to hidden separation and spalling, meaning chunks can break off. So engineers keep patching. Sealants, overlays, injections, chipped out repairs, again and again. The work is real, but it often feels like treating symptoms, not the disease. Some reports suggest even good repairs don't always stay good. In one UK review cited by researchers, about 20% of concrete repairs failed after 5 years, rising to 55% after 10 years. Those numbers help explain why engineers dream of materials that reduce the need for repeated patchwork. Now the big question, the one that sounds like science fiction but isn't. What if the material could do some of that repair by itself? What if concrete and polymers could respond to damage the way skin responds to a cut? First twist, ordinary concrete can sometimes heal small cracks on its own. Researchers call this autogenous healing. It means the material uses its own leftover chemistry to close tiny gaps, especially if water is present. In lab and field studies, tiny often means hairline cracks around 0.15 millimeters wide or less, where minerals can gradually fill the gap and cut down water leakage. Wider cracks usually need extra help. One way it happens is continued hydration. Not all cement particles react on day one. If water later enters a microcrack, some unreacted cement can hydrate and create new solid material inside the crack. Another way is carbonation. Dissolved calcium from the cement reacts with carbon dioxide in water and forms calcium carbonate, a stone-like mineral that can fill part of the crack and improve water tightness. But there's a limit. Autogenous healing works best for very small cracks, and it depends on the right moisture conditions. If a crack keeps opening and closing or gets too wide, concrete's natural self-repair usually can't keep up. That limit is where the new idea begins. Don't hope for healing, design for healing. Give the material tools to fix itself, the way your body uses clotting, scabs, and rebuilding tissue. Engineers have tried many paths, but most fall into a simple trio: release a glue when a crack forms, grow a filler inside the crack, or keep cracks so tiny that nature finishes the job. Let's walk through them like a story, because each one solves a different part of the same mystery. How do you stop a crack from becoming a collapse? One approach is to hide small containers in the material, like tiny bandages waiting for an injury. When a crack cuts through, the container breaks and releases a healing agent that fills the gap and hardens. This capsule idea became famous in polymers first. A classic experiment used microcapsules filled with a liquid resin. When a crack formed, the resin flowed out and cured, restoring strength in test samples. Concrete versions swap resin for things that make sense in cement, mineral agents, or chemicals that create solid products inside the crack. Some designs also use small tubes or vascular channels, so fresh healing agents can be supplied more than once, like a tiny blood vessel network. This is not just a lab trick. In the UK, a research team built full-size trial panels for a road project at the A465 Heads of the Valleys Highway upgrade. Their site trial used 5 panels and tested multiple self-healing techniques, including capsule-based systems and a vascular flow network. If you're used to the idea that concrete is dead, this is the mind bender. The concrete can carry a repair supply, and the crack itself becomes the trigger that releases it. Method 2 sounds even wilder. Add bacteria spores to the concrete. Spores are like seeds. They can stay dormant for a long time, then wake up when conditions are right. In bacteria-based self-healing concrete, the goal is simple. When a crack lets water in, the bacteria become active and help form calcium carbonate, often called calcite. That calcite can seal the crack, especially for small crack widths. To make it work, the system needs a safe home for the bacteria and a food source. Researchers have explored ways to protect spores inside porous particles and include nutrient compounds so the bacteria can form mineral filler when cracks bring in water. And this idea has moved beyond jars and test blocks. Commercial pilots exist too. For example, the company Basilisk publishes case studies of using a liquid repair system to reduce leakage from many shrinkage cracks in real concrete structures, including a parking garage pilot. Here's an honest reality check. Field trials are messy. In the A465 trials, the researchers talk openly about challenges and the need for improvements while moving from lab samples to real construction. That's normal in civil engineering, because the weather, the loads, and the cracks never follow a neat script. Still, the promise is huge for one reason: water. Water is the thing that makes cracks dangerous, and water is also the trigger that could start the repair. The third method is sneaky. Instead of focusing only on filling cracks, it tries to change how cracks form in the first place. Some cement-based composites, like engineered cementitious composite, also called ECC, are designed to spread strain across many tiny microcracks instead of one big crack. Because the cracks are so small, they can seal more easily through natural healing processes. This is not only theory. The University of Michigan describes the use of bendable concrete, meaning ECC, on a bridge deck project, pointing to it as a real-world use case rather than a lab-only material. In tests, researchers have measured self-healing behavior in ECC, looking at how tight microcracks can close and how water tightness can recover after cracking. Think of it like this. If you can keep the wound tiny, the body's natural healing works better. ECC tries to do that for concrete. Control the crack so it never becomes a wide-open path for water. Concrete gets most of the attention, but roads have their own self-healing story. Asphalt already has a natural ability to heal small cracks when it gets warm because its binder can flow a little. The scale is hard to picture. One review notes the global road network spans about 16.3 million kilometers. When maintenance happens on that scale, even small improvements in durability can ripple into fewer repairs and fewer disruptions. The problem is timing. Traffic loads crack the road every day, and cold weather makes the binder stiff. So researchers have explored ways to trigger healing on purpose at the right moment before cracks grow. One method is induction heating. Mix in metallic fibers, then apply an electromagnetic field from the surface. The fibers heat up, warming the binder near the crack so it can flow and close gaps. A transportation research report in Louisiana tested this idea in the lab with a road surface mix that included up to about 5% metallic fibers by weight, then applied induction heating to damaged specimens to stimulate healing. The bigger message is the same. If you can slow crack growth, you buy time. You delay the day when a road must be milled and replaced, and that means fewer closures, less noise, and fewer nights of orange cones. Now zoom out from concrete. Many buildings rely on polymers too. Paints, coatings, sealants, and composites. And in polymers, self-healing has become a huge field with both capsule-based systems and chemistries that can reconnect after damage. A key reason coatings matter is corrosion. If a protective coating gets scratched, the bare surface underneath can start reacting with air and water. Self-healing coatings aim to close those microcracks and restore the barrier, sometimes with heat, light, or moisture as a trigger. This matters for infrastructure because we often protect steel and concrete with layers, paints, membranes, sealers. If the outer layer can fix itself after small damage, the whole system may last longer. Here's the deeper reason self-healing materials have become so hot. We are building and maintaining at the same time. Many major structures built decades ago are now aging together, while traffic loads and climate stress keep rising. There's also the climate and cost side. Cement production is carbon intensive, and some research estimates cement accounts for roughly 7 to 8% of global carbon dioxide emissions. If structures last longer, we can reduce the need to pour and replace as often. That doesn't mean self-healing concrete saves the planet by itself. It means engineers are looking for a full toolbox, better design, better materials, smarter maintenance, and maybe materials that do some maintenance on their own. If this sounds like magic, remember, skin heals because it has energy, blood flow, and a living system that can keep working. Concrete is not alive, so every self-healing approach has limits, and those limits matter more than the headlines. Crack size is a big one. Many self-healing methods are aimed at small cracks because small cracks are the cracks that quietly cause long-term durability problems by letting water in. Another hard part is repeatability. A capsule can break once. A bacterial system needs the right moisture and nutrients. A vascular system must survive construction and decades of service. Field trials like the A465 panels are valuable because they reveal those real-world challenges. And then comes standards and trust. Engineers don't just need a cool demo, they need test methods, design rules, and long-term performance data. That's slow work, but it's the only way new materials become normal materials. So when will buildings heal like skin? The honest answer is in pieces. We already see field trials and pilot applications. We already use crack control strategies, and we already depend on coatings and overlays that are getting smarter. The near future is likely a hybrid, concrete that manages cracks better, plus targeted self-healing features where water tightness matters most, like tunnels, basements, marine structures, and bridge decks. And one day, the best compliment you could give a bridge might be the same compliment you give a healthy body. It took damage, it repaired itself, and you never even noticed.